So let's talk about loss functions. So where else can we tune? Activation functions, okay. Depth of network, okay. Now let's look into how to actually compute the error. And if it's not clear yet, what I mean by this is, you know how your learning system looks during training. You have some input, you put it through your network, you get some numbers, right? Depends on the weights in between in this network. People usually refer to these sort of unbound numbers as logits. And then you, if you like, depends on your problem. If you have a classification problem, you would probably push that through a softmax activation so that you get something that looks like a probability distribution. So that is the most likely class here apparently. Or if you do something else with these logits, then leave them as they are. Or if you want to adopt the logits directly, it's no problem. You have some vector of a certain size here, or even an image, some tensor of a certain size coming out here. So now what you do is you have your should be ground truth. This is your desired output. I would like that the network actually produces this. And then you just compare these two vectors. Right? This is the loss or the error between these two. And then you use this error and do your usual backpropagation with this error and plug it in your gradient. First gradient, second gradient, and so on. And then this tickles through the whole network back to the first layer, and all the weights are updated. Okay? So this is what is referred to as a loss. It's the error between desired output and your actual output. And there are various losses. So probably let's start with the most common one, or the kind of most familiar one. And this is the straightforward, the mean square error. Yeah, so the mean square error is probably the most straightforward one, you know, also from other classes. You take the difference of the result and the desired output and the ground truth for this sample and square it. That's mean square difference. For example, if you have a mini batch of inputs, so several samples which you pass through the network at once, of course you get number of samples in your mini batch losses here, and there you have to decide how you deal with those. They can be reduced to a single value, so you can either use something like a sum or a mean to represent the overall error of your network. Okay, and that quadratic function has some nice properties. It will kind of maybe overemphasize some high errors, but it's differentiable, so you can plug it directly into your backpropagation and put the error value backwards through your whole network. Okay, so there's a variant of the mean square error. So that mean square error is also known as the L2 norm. Now there's also an L1 norm, which is just the absolute value between the differences. So the L1 loss is basically, yeah, as I said, the absolute value of the differences between the current sample and the desired output. And this is most often used to allow robust regression. So that means that you want small errors to count a lot and large errors to count, but not as much as, for example, in an L2 norm. So this is very good when your training data is noisy, and your training data will usually always be noisy. So if you want to do some regression on it, then it's good to have kind of properties of this in your error function. However, the problem with this is that it is not differentiable at the bottom. So here we have a kink, so we can't differentiate. It is not smooth. And to mitigate this, you could use a soft version of L1. It's called sometimes soft shrink or smooth L1 loss. The smooth L1 loss is a bit of a hack, but it behaves basically like an L2 loss at the bottom. So it has a smooth round shape here, and like an L1 norm for, so it's here straight, so like an L1 norm for large errors. So this is obviously useful to protect against outliers and noise in your data, but obviously one problem with this loss is that it has some sort of scale or threshold here. So why should it be 0.5 here? So all your errors will depend on that scale, which is very difficult to know in advance, and most likely it will be an arbitrary choice, and you have to experiment with this to get optimal results. So a very common one is the negative log likelihood loss. So this is based on the idea that every output of your network represents a likelihood, for example, for a particular class. The logits only have some sort of scores, but if we reinterpret them to be some sort of likelihood, then we can pull in some known properties from energy-based models and probability-based math, and use the negative log likelihood to actually optimize. So this loss really aims to make the output for the correct class as high as possible, and those for the others as small as possible. So the incorrect classes get very, very small, and the correct one gets as large as possible. So nothing really restricts here the likelihood. So really the name is just here to convey that basic idea. They can be any values really. They don't necessarily need to be likelihoods. So what the equation says basically is pick the x that happens to be the correct one for one sample in the batch and make that score as large as possible. So this one here this one here also actually allows you to weigh the classes differently. This is how most of these kind of losses are implemented in, for example, in PyTorch, and you can weigh the contribution of the classes basically on their frequency. Right? So how often would you observe this class in the training set? So how rare is it? So if you expect a significant class imbalance in your training sample, for example, you can weigh them differently if few categories are rare, for example. There's a debate about what is better, to weigh the loss accordingly, or other people would rather advocate to increase the frequency of these rare examples to even that out during training, so you would have more samples of rare cases more likely picked from your training set for forming a mini batch than the more frequent ones, so that the likelihood of picking those are then evened out at the input side than here on the loss on the outside. Both is basically possible here. So very, very popular loss and well-known loss for classification is the cross-entropy loss, and this is really very popular for classification problems. It is relatively straightforward. It actually combines the log softmax and the negative log likelihood loss. So basically it says I have several weighted sums, I pass them through softmax, then take the log of those, and then I want to make the output for the log softmax as large as possible for the correct class. So when you backpropagate through the log softmax, it makes as a consequence the scores of all the other classes as small as possible. So if you do the math and put them together, the equations, and if you simplify this combination, you just get the negative score of the correct class, and then add the log of the sum of the exponentials of the scores of all the other classes to make it small. So it turns out to be relatively straightforward and simple when you work out the math here, and this is what the cross entropy loss is. It's probably the go-to choice for any classification problem you have right now with any network. So the binary cross entropy loss is a special case of the cross entropy loss. So this does not contain the log softmax because it actually falls out through simplification of the combination. It is just entropies and models and Bernoulli distribution at the end. So probabilities have to be between 0 and 1. So this loss, as I said, is a special case of cross entropy, and when you have only two classes, so this only works if you have only two classes. So it can be reduced to a quite simple function like shown here. So the BCE, you would use it to measure the error of a reconstruction, for example. In, for example, an autoencoder. So this formula assumes x and y are probabilities, so they're strictly between 0 and 1. And this has nice properties then if you have some kind of direct relationships like in an autoencoder and you want to reconstruct something. So this one is the Kullback-Leibler divergence loss. This is a relatively simple loss function, and it's used when your target is a one. So this simple formulation only works if your target is a one-hot distribution. So if y is a categorical vector. Again, it assumes that x and y are probabilities. So this has the disadvantage that it's not merged with softmax or log softmax, so it may have numerical stability issues. It is used to measure the distance between distributions. So how far, how close, how similar are these? So this is, as I said, this is a simplified version of it. It is kind of prone to numerical issues, but you would use something like this in a, for example, variational autoencoder, where you during training compare the distribution of your bottleneck, the shape of that distribution, so how it looks like, to a normal distribution. So that way you can ensure that your bottleneck will kind of resemble a normal distribution. So that's where you would use this. You wouldn't use that for a classification problem or something like that. It's really just to measure distances between distributions. So margin ranking losses are becoming a very important category of losses. So unlike other loss functions such as cross entropy loss or mean square error, whose objective is basically to learn to predict directly a label or a value or values given an input, the objective of ranking losses is to predict relative distances between inputs. So this task is often called metric learning, and so ranking loss functions are very, very, very flexible in terms of training data. We just need a similarity score between data points to use them. So that score can even be binary, similar or dissimilar. Okay. So to use a ranking loss function, we first extract features from 2 or 3 different input samples and input points and get an embedded representation for them, so some logic vector. Okay. So then we can actually define a metric function to measure the similarity between these representations. For instance, a Euclidean distance would work, or some geodesic distance. Usually would work with a Euclidean distance, just take the difference of these. Finally, we train the feature extractors to produce similar representations for similar inputs. Yeah, in case of the inputs are similar, I want to have them kind of close. So the loss actually has a small error if the network produces similar representations for similar input data sets. So it brings these kind of similar players, it brings these data points closer together. Then we train the feature extractors so for distance for representations that are not similar, where we know already that they are not similar, we try to make them as dissimilar as possible. So these 2 samples here, we want to put them away, and for that I just draw samples, right? I have a kind of additional meta ground truth where I know for every sample a kind of similarity matrix to every other sample, how similar they are, and as I said, this could be binary, it's similar or not similar. And here in this case, we don't even care about the values of the representation, only about the distances between them. However, this training methodology has demonstrated to produce powerful representations for different tasks, despite not directly looking at these differences. So margin errors are an important category of losses. If you have 2 inputs, this loss function tells you what one input so says you want one input to be larger than the other one. It doesn't matter how distant they are. The only thing you want to optimize is that if you compare similar and dissimilar, that the similar ones are smaller than the distances to the dissimilar ones. So you want the score for the correct category larger than the score for the incorrect categories by at least some margin. If it's larger than this margin, then you say accept. That's good. So so if, for example, y times x1 minus x2, simple example, is larger than a given margin, then the cost is 0. So you won. They are somewhere, you don't care where exactly they are, but they're far away, they are at a safe distance for your whatever classification or whatever you want to do with it. So if it's smaller, the cost increases linearly, as shown here in the equation. So if you were to use this for classification, you would have, for example, x11, the score of the correct answer, and x2, the score of the highest scoring incorrect answer. Okay, so you would pick the highest scoring incorrect answer and the score of the current sample and build the difference here, and you want to make sure that this is larger than a certain margin, than a certain given distance. So if it is used in energy-based models, these loss functions pushes down on the correct answer. We won't discuss energy-based models in this lecture, but you can do some reading about this. It's, in my opinion, just a different view on the same thing with a more sound and solid theoretical foundation. The objective is the same. We want to have a good numerical representation of whatever input we get. So there's a variant of, there are several variants also of the ranking margin losses. And this is, for example, the triplet loss, which is popular choice by now. And so in the previous one, we used pairs data points. Now here we use 3 data points. And this loss is used for measuring a relative similarity between samples. So this is really used a lot for metric learning if you want to refine some predefined metric. For example, you put 2 images with the same category through a CNN and get 2 vectors with the previous loss, and here you put 3 through a CNN and you get 3 different representations. So this triplet loss tries to send the first distance towards 0, and you would pick a sample that is so you have your test sample, and then you pick a sample that is in the same category. So you want these 2 to be close. So you pick this, and if this is smaller than a margin, then you say loss is 0. That's fine. And then you pick a negative example as before, probably the wrong example that has the highest score, or even probably higher than the true category. So you put that in and try to make it larger. So if this is at least larger than a margin, then loss is 0. Otherwise, it's the linear loss. Really, the only thing that matters is that the distance between the good pair is smaller than the distance between the bad pair here. So XA and XP should be smaller than XA and XN. So this actually, that idea is has been around since a while. So this was originally used to train an image search system for Google. Nobody knows if they still use the same algorithm. But at that time you would type a query into Google, and it would encode that query into a vector, and then you would compare that vector to a bunch of other vectors that have been extracted from images. So, and to shape these representations from the images, you would actually train that systems like this image retrieval system, and you would try to find the vectors that are closest to the vector of your query, and for that you only have relative distances. So you would use a loss like this and punish the system if the distances to the negative bad samplers is smaller than the distance to the positive samplers, and the final aim is really to have these arranged like shown in this figure from the original paper here. So where you really try to bring the positive ones closer and the negative ones away from that margin. You don't, this is the margin, right? You don't care where they end up here in the margin. You only care about this beyond the margin, this within the margin, and then you're good. So there's not a group of losses, so it's more like about similarity measurements. So the cosine embedding loss, for example, is used for measuring whether two inputs are similar or dissimilar, using the cosine distance. So input can really mean some kind of latent representation, but the input to this loss gives you just a similarity metric between these two. So if you think about this in another way, 1 minus the cosine of the angle between the two vectors, input vectors, or some latent representations, is basically some sort of Euclidean, normalized Euclidean distance. And really the advantage of this is that whenever you have two vectors and you want to make their distance as large as possible, it is very easy to make the network achieve this by making the vectors long. So in this cosine representation, everything is just on a sphere. So you prevent the network from making vectors just long to get them far apart from each other. So for positive cases, this loss tries to make the vectors as aligned as possible. For negative pairs, this loss tries to make the cosine smaller than a particular margin again. So the margin here could be some small positive value. And really what you will end up with this is that probably your positive samples will land somewhere in the poles, and then you want to push all the negatives away with it, will probably end you up in the rest of the sphere somewhere. You know, there are lots of points in the poles in a cosine representation, and all the other points are distributed across the sphere. So in a high dimensional space, there is a lot of area near. There's even more area near the equator of the spheres than in 3D. So after normalization, all your points are now normalized on that sphere. What you want is samples that are semantically similar to be close, right? So the samples that are dissimilar should be orthogonal. So you want them to be opposite. So you want all the similar ones somewhere in the poles, and all the dissimilar ones are somewhere in the equator, 90 degrees away from you. So rather, on the equator there is a very large amount of space for you, so to make these margins more, and you can really take an advantage of the properties of this kind of cosine embeddings, especially in high dimensions where you want to put them away from each other or close to each other as much as you like, without blowing up the representation, the magnitude of your vectors actually. So this is used in Siamese networks a lot. We have spoken about them, but if you read about them, they usually use to compare the output of two different representations. They don't use a Euclidean distance, they rather use this normalized Euclidean distance, which is the cosine embedding loss. So what do we learn from this? The choice of the loss depends very much on the desired output. So very much on your general problem. Are you doing classification, regression, reconstruction, any of those? Then you would probably already restrict on a class of losses what to use. And then it's probably the same as for the activation function. Start with the simplest or the kind of most common choice, and then work your way backwards to improve. Again, the loss is only as good as your training data distribution from which you learn. So if your training data is bad, tinkering around with the loss won't help you either. So loss functions and how to design them are a very hot topic of research. If you want to go on and do some research in this area, you probably will at some point be touching new functions, how to represent the error of any sort of learning system. Not so much how to build an architecture, but this is currently more where people look into. So again, a loss, an error informs really how the overall learning system behaves during training and how it optimizes, because that one error, that one value is really the thing that informs the change of all the weights in the backward pass. So that really, don't get scared by the equations. If you look closely, the underlying ideas are actually relatively simple, especially for the simple losses, and one can argue around the manifold of the representations and how this is structured and the geometry of it. This is where all the research currently goes in, how to represent these manifolds. So far, these loss functions usually make the assumptions of local linearity in the representation manifold, which might or might not be the case or accurate. So we don't know really at this point. The idea itself is just how do you characterize difference between your samples.